Hello everyone, this video is going to be all about the full adder circuit, a final project presented to the Faculty of College of Engineering, Mindanao State University, Iligan Institute of Technology, in complete fulfillment of the requirements for the course Logic Circuit and Switching Theory Laboratory or EST 121.1 by Globally Apo Lastimosa, yours truly, Heine Eve S. Manunday, Shaira Luna M. Parohinog, and Marian Margaret Takbas. This final project will look into the technical aspects of designing and building a full adder circuit with a focus on the use of the integrated circuit or IC 74LS83N. This integrated circuit, which functions as a 4-bit binary full adder, plays an important part due to its efficiency and compact design designed for the binary addition. The parts needed to assemble the full adder circuit and its specifications are 1K resistors, a breadboard as a platform for constructing the circuits, connecting wires used to create connections between different components that are used in this project, green light emitting diodes as an indicator for the SAM outputs, blue light emitting diodes as an indicator for the carry out, 5 voltage power bank used to supply voltage in the circuit, and lastly, the 74LS83N IC, which is a high-speed 4-bit binary full adder IC with carry-out feature.
Now, I will be discussing the following step-by-step process for building a 4-bit binary full adder circuit with IC 74LS83N. The first step is the IC should be placed on the breadboard. Place the IC 74LS83N on the breadboard with caution. Make that pin 1 is indicated by the notch or dot on the IC, which should be correctly aligned. Second step, link the power source. Attach the positive 5V power supply to pin 5, the VCC on the integrated circuit. Attach pin 12, the ground pin, to the ground. The third step, join binary inputs A and B together. To depict the 4 bits of input A, connect pins 10, 8, 3, and 1. The next step, to depict the 4 bits of input B, connect pins 11, 7, 4, and 16. Next step, establish carry-in. If this is the first adder, connect pin 13, the C0, to the ground, or in the event of a cascading adder, to the carry-out of the previous complete adder. Next step, link LEDs for output visualization. The binary sum and carry out can be seen with LEDs by connecting them to the appropriate output pins via current limiting resistors. Some pins 9, 6, 2, and 15 should be connected to an LED via resistor, then to the ground. The C4 or pin 14 should be connected to the ground, another LED, and a resistor. Next, check the connections. Make sure there are no loose wires or improper connections by double-checking every connection. Number 7, power up. Applying the positive 5V power supply will turn on the circuit. The 8th step, examine results to see the binary sum and carry out. Look at the LED that are attached to sum and see out. And lastly, test using various inputs. To ensure the circuit is functional, test it with various input combinations if your switches are binary input switches.
So to check whether our binary adder is right, we're going to be trying to input the values in the truth table and see if the outputs are correct. So this here are the LED indicators. So this is the indicator of sum 4, sum 3, sum 2, sum 1, and the carry. So this here are the switches of A, and here is our switches of B. So here is switch 4, switch 3, switch 2, and switch 1. And this here is switch B4, B3, B2, and B1. Okay, so based on the truth table, we have to set all the values to 0, which is what exactly is happening in our circuit right now. So all the values are 0, which means all the sum and the carry is also 0. So next is A4 and B4 must be set to 1. So this is A4 and this is B4. And based on the truth table, the value of S3 must be 1 and the rest must be 0, which is correct. So next is the value of A3 and B3 must be set to 1. So this is switch A3 and this is B3. And according to the truth table, the sum 2 must have a value of 1 and the rest is 0, which is correct. So next is A3 and A4 must be set to 1. So this is A3, this is A4 must be set to 1. And also B3 and B4 must be set to 1. Now, according to the truth table, or the output of the truth table, sum 2 and sum 3 must light up and the rest must have a value of 0, which is correct. So this is sum 3 and this is sum 2. So next is A2 must be set to a value of 1 and B2 must have a value of 1 also. So this is A2 and this is B2. Now, according to the truth table, sum 1 must have a value of 1, which is correct, and the rest must be 0, including the carry. So next is A2 must have a value of 1 and A4 must have a value of 1, while B2 and B4 must also have a value of 1. B2 and B4. So according to the truth table, sum 1 and sum 3 must have a value of 1, which is correct, sum 1 and sum 3, and the rest must have a value of 0. Yes. So next is A2 and A3 must have a value of 1. So this is A2 and this is A3. And B2 and B3 must have a value of 1 also. A2, B2 and B3. So based on the truth table, S1 and S2 must light up or must have a value of 1 and the rest is 0, which is correct. Okay, so next is A2, A3, and A4 must be set to a value of 1. A2, A3, and A4 must have a value of 1, okay? And B2, B3, and B4. So B2, B3, and B4 must have a value of 1. So based on the truth table, sum 1, sum 2, and sum 3 must turn on or have a value of 1, which is what is happening in our circuit right now. Okay. Okay. Next will be A1 must be set to a value of 1 and B1 should also be 1. So, based on the truth table, we must have a carry. So, which is why our blue LED lit up and the rest is 0. Next is A1 and A4 must be set to 1, and also B1 and B4, B1 and B4. And based on the truth table, sum 3 must light up, which is this, and also the carry, which is this. Next will be A1 must have a value of 1, also A3. And in the B switches, B1 must have a value of 1 and also B3. And based on the truth table, sum 2 must light up and also the carry, which is correct. Okay, next is A1, A3, and A4 must have a value of 1. A1, A3, and A4 must have a value of 1. And then B1, B3, and B4. B1, B3, and B4. So based on the truth table, sum 2 and sum 3 must light up and also the carry, which is correct. So next is A1 and A2 must have a value of 1, A1 and A2. And also B1 and B2. So B1 and B2. So based on the truth table, S1 must light up and also the carry, which is correct. So next is A1, A2, and A4 must have a value of 1. A1, A2, and A4 must have a value of 1. And in the B part, B1, B2, and B4 must also have a value of 1. B1, B2, and B4 must also have a value of 1. So based on the truth table, sum 1 and sum 3 must have a value of 1, including the carry, which is correct. Next is A1, A2, and A3 must have a value of 1. So A1, A2, and A3 must have a value of 1. Also, B1, B2, and B3. So based on the truth table, sum 1 and sum 2 must have a value of 1, and also the carry out, which is correct. Lastly, A1 to A4 must be set to 1. Also B1 to B4. Okay, so based on the truth table, sum 1, sum 2, and sum 3 must have a value of 1 and also the carry out, so which is correct.
Now, let's uncover what we discovered about the full adder circuit. We'll explore the sum output and carry output, unraveling how it handles binary addition with input. Plus, we'll break down its behavior using a simple truth table. So, sum out, the addition outcome of the two input bits A and B and the carry input C in is represented by the sum output S of the entire adder circuit, depending on the inputs. It can have one of two binary values, either 0 or 1. The least significant bit, LSB, of the result is given by the sum output. Then carry output. If a carry has happened during the addition operation, it is indicated by the carry output of the complete adder circuit. Additionally, it may assume the binary values of 0 and 1. In multi-bit operations, a carry must be transmitted to the subsequent higher order bit if C out is 1. The truth table. Truth tables which list all conceivable combinations of input values A, B, and Cn, and their corresponding outputs C, Is, and Cout, can be used to characterize the behavior of the complete adder circuit. The truth table facilitates analysis and functional verification of the circuit by displaying the relationships in logic. To sum up,
The 4-bit binary full adder is an essential part of digital circuit design that allows adding binary numbers for a variety of uses, such as memory addressing, arithmetic operations, microprocessor construction, data processing units, error detection, and correction, binary coded decimal or BCD, sequential circuit design, and many more. It plays a fundamental role in digital computation and makes a substantial contribution of many electronic systems. Enthusiasts and learners acquire hands-on knowledge about building digital circuits, diagnosing issues, and functioning of crucial parts. Larger arithmetic and logical processes in digital electronics can be understood due to a bit binary full adder, which forms the basis of increasingly advanced digital systems.